Our next topic is properties of rational number. So the first property in the list is closure property. So you're going to see closure property for addition, multiplication, division and subtraction. Sorry, I messed up that. So what is closure property? It's basically when we have a natural number, suppose, and another natural number. So any operation which we perform on those two natural numbers like addition, subtraction, multiplication, division should give the result as natural number. If it does, then the closure property is obeyed, it holds true, and if it does not, then it does not hold true. Now what is addition? Addition, closure property of addition of natural numbers we are going to see. So let's take for instance, we have two natural numbers, say 2 and 3. We add them and we have another number that is 5. So friends, is 5 a natural number? Yes, it is. So 5 is a natural number. Then we look for whole numbers. Suppose we take a whole number, say 2 again, and another whole number 0. So 2 plus 0, 2. It is again a whole number. Then we see for integers. If we have an integer, say minus 1 plus say minus 2. So this becomes minus 1 minus 2, that becomes minus 3. Is minus 3 an integer? Yes, it is. So, closure property of addition for natural number, whole numbers and integers holds true. Now coming to the focus point, that is the rational numbers. Let's take a rational number such as, let's take 2 by 3. 2 by 3 plus 1 by 3. Now 2 by 3 plus 1 by 3, since the denominator is same, we look at the numerator. 2 plus 1 gives 3 and denominator as it is. So this gives us 1. Is 1 a rational number? Yes, we have learned in the previous video that 1 is a rational number. So it holds true. So addition of natural numbers, whole numbers, integer and rational numbers is closure for addition. Now looking for subtraction. Subtraction of natural numbers. Now what we do is we take a rational number, say 2, and another rational number which is smaller than 2, we take it as 1. Okay? So the answer comes out to be 1. Is 1 a natural number? Yes, 1 is a natural number. But what if we turn it the other way around? What if this number is greater than this number? Let's try it out. Say 1 minus 2. So 1 minus 2 gives us minus 1. Is minus 1 a natural number? No friends, it is not. So closure property does not hold true for subtraction of natural numbers. This we have seen, it is not that if it is applicable in this case and it is not applicable in this case. Even if it is not applicable in one of the cases, we will simply say it is not applicable. We won't say that it is applicable for one case and not applicable for other. So we look for it, or conditions apply, no conditions apply. In maths, if it does not hold true for one, it does not hold true for any category of the same number. Taking for whole numbers, similar example, taking 4 minus 0 is equal to 4, and taking another number, like reversing it, we have 0 minus 4, that is minus 4. So what we see here is that minus 4 is not a whole number. So closure property does not hold true. Whole number minus whole number does not give a whole number. Okay. Now looking for integers. Let's take an integer, say minus 2, and another integer, since we are subtracting minus sign. Another integer, let's take as 3. So another integer 3. So this gives us minus 2 minus 3, that is minus 5. Guys, is minus 5 an integer? Yes, of course it is. So minus 5, closure property holds true. What if we reverse the digits? In this also it holds true, in this it does not. On reversing the digits, so we say it does not hold true. Now we look for it after reversing the digits. So reversing the digits, 3 minus minus 2 is equal to 3 minus minus plus is equal to 5. Is 5 an integer? Yes, it is. This we have learned in the previous video. Please refer to that. Now what we see is closure property holds true. Holds true for integers. So it holds true. Okay. Now for rational numbers. Let's take a rational number, an easy one. Let's take 4 by 5 minus let's take 2 by 5 again. Easy numbers. So 4 minus 2, since denominator is same, we consider the numerator. 4 minus 2 gives us 2 upon 5. Is 2 by 5 a rational number? P by Q form where Q is not equal to 0. It is a rational number. So it holds true for this case. Now let's reverse the digits. Let's take 2 in the front by 5 minus 4 by 5. What we see here is 2 minus 4 gives us minus 2, denominator remaining the same. But this we have learned that P can be any integer. It can be minus 2, it can be plus 2, it can be 10,000, 100, 10, whatsoever number it wants to be. The only condition is this number should not be equal to 0. Q should not be equal to 0. Is this condition satisfied? Yeah. Now we move on to multiplication. For natural numbers, if we multiply a natural number with another natural number, say for instance we have 2 multiplied by another natural number, say 4, the result is 8. Is 8 a natural number? Yes, it is. So it holds true. Then we take for whole numbers. Let's take a whole number, say for instance 0 into, that is multiplied by another whole number, say for instance 8. So 8 into 0 gives 0. Is 0 a whole number? Yes, 0 is a whole number. So it holds true again. Now for integers. If we multiply an integer with another integer, that is, if we multiply, say, minus 2 with minus 3, what we get is 6. Is 6 an integer? We all know it's an integer, so it holds true again. Now take rational numbers, which is our focus. So a rational number, say 2 by 5 into another natural number, say 6 by 11. So how do you multiply fractions? Say minus 6 by 11. Because rational numbers have both negative and positive fractions. So minus 6 by 11. So 2 into minus 6 gives us minus 12. And 5 into 11 gives us 55. Is this a rational number? See, P can be any integer. So P is any integer, satisfy the main condition. 55 not equal to 0. Q is not equal to 0. This satisfied. Minus 12 by 55 is a rational number and commutative laws hold true. Now we see for division. Okay. Let's take a natural number. Say for instance we have 10. 10 divided by 2, which is again a natural number. Does this give us a natural number again? It gives us 5. But this was a case when 10 was exactly divisible by 2. What if we have a number such as 10 divided by 3? See, 10 and 3 both are natural numbers, but what we see is that the result is not a natural number. So it does not hold true. The commutative law for division of natural numbers does not hold true. Now we see for integers. Now we see for whole numbers. Whole numbers. Let's take for instance whole number, say 10 divided by 0. So 10 divided by 0 gives us 0, which is a whole number. But if we take another case, that is say 0 divided by 10. 0 is a whole number, 10 is another whole number, but the result which we get is not a whole number. It is not defined. So it does not hold true for division. The commutative law of division for whole numbers does not hold true. Now we see for integers. Let's take an integer, say minus 20 divided by 4. So minus 20 divided by 4 gives us 5. Minus 5. But this is exactly divisible by 4. But what if we have a number such as minus 20 divided by, say, 13? Does this give us an integer? It does not. So it does not hold true for the commutative law for division of integers does not hold true because the resultant is not an integer. Taking it for rational numbers. Say we have a rational number 2 by 3 divided by 0. If we divide this number by 0, the answer which we get is 0. But what if we have these places interchange, that is 0 divided by minus 2 by 3. When we have such a case, what we see is the product is not defined, which does not include a rational number. So the product is not included in rational number, therefore it is not commutative.